Okay, now we want to talk about tensile and compressive strain and deformation. Deformation is basically dimensional change. And if dimensional change happens in the material, we call it deformation. Uh, Deformation could be either tensile or compressive change. If you guys remember, uh, if we had a steel pole and if we compress it, after a while it's gonna be compressed and it's gonna be deformed. And if it is under tensile, it's gonna elongate. All right, and it always deformation is indicated with the Greek word delta, and this is really important from now on. We have the term strain. Okay, what is a strain? Strain is the total deformation over the original length. Strain could be elongation or compression or any form of deformation. We call it a strain. And it is indicated by epsilon. So total deformation over original length is called a strain. All right. And in US customary system, a strain is inches per inches. But in SI uh, customary system, it is millimeters over millimeters or meters over meters. Example 9.14. Compute the total elongation or deformation for a steel wire 60 feet in length if the strain is 0.00067 inches. Right, so we want to see what's the total deformation, and as we had it in our formula, epsilon equals delta over L. All right, what do we have? The question says compute the total elongation deformation for a steel wire 60 feet in length, and the restraint is so strain is 0.00067 inches per inches, and the length is 60 feet. All right, so what do we have and what do we want? We have epsilon, we have L, so we want the delta. So we can just easily change the formula to calculate the delta that we want. So delta equals epsilon L. So epsilon equals 0.00067 into 60 feet. But we don't want feet, we want inches. So every 1 feet is 12 inches. So 60 into 12. And the answer is 0.00067 0.482 inches. Alright, as we talked about it before, the strain is the deformation of the material. And now we want to talk about shear restraint. Okay, for example, if we have a block on the ground, if there is a force, and the force is this direction, what's gonna happen? After some times, the block is gonna deform. After some other time, the block is gonna deform in this way. And as we talked about it before, because this is in equilibrium, if there is a force P to this side, the material itself produces a force P to this side as well. Okay. So, if we call this the length of this material, and obviously the deformation is gonna be this much, all right? Call it delta in here, and since it is shear strain, we call it delta S. Okay, and as the formula that we have it before, epsilon equals delta over L. Epsilon S, or epsilon of shear strain, equals delta S, delta of shear strain over dl. Okay, and just one more thing, one last thing. Here there is gonna be an angle. We call it theta. Okay, theta angle. If we could calculate the tangent theta equals same delta S over L, and as we had it before, delta S over L is epsilon S. So this, the tangent of this angle equals the shear strength of this material, this situation. Okay, and always shear strength is a very small amount, okay, because the materials don't have the shear strength of very big shear strength. They always have a small shear strength. Example 9.15. In this figure, assume that the load P, this is the load P, is applied at the top of the block. It displayed the top of the horizontal distance of 0.0024 inch with respect of the bottom of the block. Assume that the height L of the block is 1.4 inch. Compute the shear strength. It says that this distance is this distance, which is delta S is 0.0024 inch. Where did I get that? Again, it says In this figure, assume that the P is applied at the top of the block and it displaces the top of horizontal distance of 0.0024 inch with respect to the bottom of the block. So the distance that it moved this block is this much. So as we talked before, the distance is delta S, right? And assume the height, which is L, is 1.4 inches. Okay, what is the shear strain? So shear strain equals delta S over L. So shear strain equals, what was delta S? 0.0024 over 1.4. The answer is 0.0017 inches over inches. That's our shear strain. 9.6 relationship between stress and strain, or Hooke's law. In most engineering materials, there is a relationship between stress and strain. It means increase in stress equals increase in strain. But it has a proportional limit. Increase in strain in proportional to increase in strain. It means that increase of stress has the proportional increase of strain to a limit. All right, and we will talk about that limit in next chapter, chapter 10. We call this a Hooke's law. So what does this mean? It means that, for example, if we have for example, we do have force of P, which is put on a material, for example, on a stain, on a steel, okay? It has causes a stress, and it causes strain, okay? So if it causes this much stress on this material, it is going to cause this much strain. Call this, if it causes this much stress, it is going to call this much strain. And if it causes this much stress, sigma B, it is going to cause this much strain in our material. Alright, so as this is proportional, we can always say this, because it is proportional, right? Sigma A over equals sigma over B, because it is constant. Okay, and we call this the module of elasticity of each material, or a Young modulus of each material. All right, and the Young modulus, or module of elasticity is, we can write this formula for it. So modulus of elasticity, or Young modulus, equals stress or sigma over strain or epsilon. So if you want to calculate the Young modulus or modulus of elasticity, we have this formula to calculate it. All right. So in US customary system, the Young modulus is calculated and is told by pound in cubic inches, and we call it PSI. In SI, it is in Pascal or megapascal. Modulus of elasticity of a steel is 20 million psi or 30 million psi in this book. And modulus of elasticity in the same in SI is 200 megapascal or 207 megapascal. In this or means because we have different steel properties, so we have different modulus of elasticity. And we can see the modulus of elasticity of some common enduring materials in Appendix G as well. And we have another calculation that we can make. It is called modulus of rigidity, which is called G. And modulus of rigidity is calculated by this formula, which is pretty easy. We learn shear stress over shear strain. And this is how you calculate modulus of rigidity. We will talk about modulus of elasticity, Young modulus, and Hooke's law in chapter 10 in extent. Alright, example 9.16. It says a 24-inch long bar with a cross-section area of 1.0 inches square is subjected to an actual tensile load of 10,000 pounds. 10,000 pounds. Shown in this figure. Compute the stress, strain, and total elongation of the bar material is if the material is steel with modulus of elasticity of 29 million psi, aluminum with modulus of elasticity of 10 million psi, and titanium with modulus of elasticity of 16,005,000 psi. Assume the proportional limit of each material to be as follows: steel 34,000 psi, aluminum 34,000 psi, and titanium 125,000 psi. So let's see what we have first. Okay, so we have the P of 10,000 pounds, and we have A of 1.0 inches squared. And what do we have? Also, we have modulus of elasticity of steel, which is 29 million psi, modulus of elasticity of aluminum, which is 10 million psi, and modulus of elasticity of titanium, which is 16 million 5,000 psi. All right, so first of all, we want to see what's the stress on each material. So we're gonna say sigma of total equals P over A. So sigma of total equals P, which is 10,000 over A, which is 1.0 squared. And the stress for each material is the same, 10,000 psi. So this is the stress for all the materials. All right, now we want to compute the strain for each material. First of all, if you want to compute the strain for steel, so just gonna write it down here. Steel, right? So we can compute this stress of strength of steel using this formula as we had it before. So if you want to compute the epsilon of steel equals total over modulus of elasticity of steel. All right, so it is 10,000 psi and 29 million psi. The answer is 0.0000345. And for aluminum, equals, so L equals 10,000 over 10 million psi, and the answer is obviously 0.001. And calculate the strain for titanium. Same equation. And if we change the equation, we're gonna have epsilon titanium equals again 10,000 psi over 16, 5,000 psi. So the answer is 0.0000606. Okay, and we want to compute the total elongation for each material as well. So we can use, obviously, this equation. Epsilon equals elongation or length. Okay, and now we have length. We have epsilon for each material, and the length is 24 inch. We don't have the delta, so delta equals epsilon into L. Okay, for aluminum, delta equals epsilon to L. Epsilon, which is 0.000345 into L, which is 24, equals 0.00828 inches. So this is the answer. And for aluminum, delta equals epsilon into L. So 0.001 into 24 equals 0.0240 inches. And the last one for titanium, delta equals, answer has 0.00606 to 24 inch equals 0.01454 inches. Right, and as we can see, the strain in titanium bar is approximately twice the steel bar, and the total deformation of aluminum bar is 3 times larger than steel bar. All right, so we can calculate that the stiffness of the steel is significantly greater than aluminum and titanium. It is safe to say that modulus of elasticity is sigma over epsilon. All right, and as we had it before, sigma equals force or length. Okay, and epsilon equals delta over L. All right, so it's safe to say that P over A and delta over L. So we could say, if we do some mathematical equations here, we could say PL into A delta. So far into far, close into close. PL over delta. So modulus of elasticity is PL over A delta, right? So as we discussed before, P is the total applied external axial load, and L is the length of the member. It could be in inches or millimeters or meters. A is the cross-sectional area of the member that we are talking about, and the delta is the total deformation of the material, and obviously E is the modulus of elasticity. Example 9.17. A tensile member in a machine is subject to an actual axial load of 5,000 pounds as shown in this figure. So axial load 5,000 pounds. It has a length of 30 inch. So the length is 30 inch and is made from steel tube having the outside diameter of 3/4 and the inside diameter of half an inch. Compute the tensile stress in the tube and the total axial deformation. Assume modulus of elasticity of 29 million and the proportional limit of 34,000 psi. All right, so the cross section of the whole area is calculated using this. So we want to calculate A, and our formula was pi 4d squared equals pi 4 2 minus d 1 equals pi 4 as 0.7854 into, so what was outside as 3/4, so 3 divided by 4 is 5 inches minus 1 divided by 2, 0.50 inches. So the area is 0.245 inches square. All right. And now we want to calculate the axial deformation or elongation. So as we had it before, the formula I just explained it to you, modulus of elasticity is PL over A delta, right? Now we want to know what's the deformation. So deformation is delta, and if we just change these two, I'm gonna say PL over AE. So we have all the numbers. P, which is 5,000 pound, in L, which is 30 inches over area 0.245 inches into the modulus of elasticity, which is 29 million psi. The answer is 0.0211 inches. All right. And now we want to calculate the tensile stress developed and verify that it does not exceed the proportional limit. So the sigma of total equals P over A. So how much was P? 5,000 pound over A was 0.245 square. The answer is 20,400 psi. All right. And if we look at the question, the limit proportion was 34,000 psi. So we haven't reached the limit, so it's okay. And the answer is correct. Okay, example 9.18. A force of 66,700 Newton is applied to a steel wire 7.5 meter in length. The tensile stress is in the wire must not exceed 138 megapascal, and the total elongation or deformation must not exceed 4.5 millimeters. Compute the required diameters of the wire, and we should neglect the weight of the wire. Should use the modulus of elasticity of 200,000 megapascal and a proportional limit of 234 megapascal. So let's see what we have. we have, let me write it down. Great. We have P, if I'm not mistaken. Yep, we have P of 60. 6,700 Newton. We have L of 7.5 meters. We have modulus of elasticity of how much was it? 200,000 megapascal. Right. So the required cross-sectional area is calculated based on the allowable tensile stress of 138 megapascal. So required area is P sigma total. So which was P was 6,700 Newton, and the sigma T or sigma O was 138 megapascal. These are numbers that the question gave us. So we have actually sigma TL. TL is 138 megapascal. You want to convert it to Newton per square meter, so you have to do this Newton per square meter. So the answer is 48.6 and 10.6 meters. Or we could say easily 48.6 meters square. All right. So the required cross-section area is calculated based on allowable total deformation, and we can use the equation that we just talked about. So we can say required A equals L to delta E. Right? So P was 700 Newton. L was 7.5 meters over the total deformation, or delta was 4.5 4.5 what was it, 4.5 millimeters, but since we have meters in here, I have to change it to meters, and the modulus of elasticity was 200,000. If we want to convert it to megapascal to Newton per meter, we have to convert it to meters. Right. And A is 0.0558 n point minus 3 10 to the power of minus 3 square meter, or we can call it 55.8 meters square. All right. And so they have two areas. All right. The larger of two areas is 55.8. All right. So use bigger one. All right. And say A equals pi 4 squared, right? Say D equals A pi square is 0.784, right? So how much was our A? A is 5.8 over 0.7854. The answer is 0.43 millimeter, right? And we have to check to ensure that the tensile stress developed is less than the proportional limit. How much was our proportional limit? The proportional limit was 234 megapascal. All right. So sigma T equals P over A. So T equals P was 6,700 Newton over 5.8. But this is Newton, this has to be in cubic meters. Right? Answer is 22 Pascal. And how much was our proportional limit? Is 234 megapascal. This is 120 megapascal, pascal to megapascal. All right. So this is bigger, so our answer is correct. So this is the example 9.19. A copper wire 150 feet long and 1/8 inch in diameter is suspended vertically from its upper end. The unit weight of the copper is 550 PCF. Compute A, the total elongation of the wire due to its own weight. B, the average strain due to its own weight. C, the total elongation of the wire delta, which includes the elongation due to its own weight if a weight of 70 pounds is attached to its lower end. And finally D, the maximum load P that this wire can safely support at its lower end if the allowable tensile stress is 12,000 psi. All right, so let's do it. Hey, so the weight of the wire is equal to the total volume times the unit weight of the copper. All right, so the total weight equals pi 2 right, into L into 550 pounds over feet of cubic feet. All right, what was 550? It was the unit weight of the copper. All right, so it is pi into 0.125 chance to what was 125 since the diameter, the question said the length of the wire was 150 feet and the diameter is 1/8. So 1 divided by 8 is 0.12524. If you want to change the inch square to feet cube, we have to convert it. This is how we convert it. We have to multiply by 144 inch into feet square. Okay, multiply by 150, which was length, into 550 the answer is 7.03 pound. Right, so what's the area of the copper? So the area is pi 4 d2 and d2 is d is 1/8, so the area equals 0.0123 square. Now we want to know the total elongation. For total elongation, we need modulus of elasticity of the copper, which we can find in appendix G of the book. And if we go there, we're going to see the modulus of elasticity of copper is 15 million psi. Right? Now, I'm going to say sigma equals, just, I have to tell you guys something. If the question ever says that our material is suspended vertically from its upper end, we always have to consider half of the force. All right, so always consider half of the force into L A E. This was the last formula that we talked about. PL over AE. Okay, we have all the variables, so our P, which is the total weight, is 7.03 divided by 2, and our length was 150 feet, but we don't want feet, we want inch, so we multiply it by 12 inch, and our area was, as we calculated, 0.0123 just square, and our modulus of elasticity is 15 million psi. So, why did I say sigma? Total elongation. Our total elongation is, if we calculate this, and it's going to be 0.0343 inches. Right? So this was part A. Let's go to part B. Part B says the average strain due to its own weight. Right? So just write it down with different pen. B, strain. Equals okay. So strain epsilon equals 0.0343 inches, or L, how much was L? 150, but we don't want feet, we want inch, right? 12 inches feet equals 0.00019. Okay. Part C. Part C says the total elongation of the wire delta, which includes in the elongation due to its own weight, if a weight of 70 pounds is attached to a slower end. So we have the weight of 70 pounds attached to its lower end. So we have elongation C. Again, L over A equals. So we don't have its own weight. If it's we have its own weight, we have to divide the weight by 2. But since we don't have its own weight, we have extra 70-pound weight. We don't divide it by 2. So the weight, the extra weight is going to be 70 pounds, and L is 150 feet. We want an inch, so multiplied by feet 12. I want to make feet to inch, right? And A 0.0123 square inch into modulus of elasticity, which was 15 million. The answer is 0.683 inches, right? So because 70 pounds was added to the actual weight, so we're gonna have total delta, which was 0.683 inches plus the own weight, 0.03 inches. The answer is 717 inches. What is this number? This number indicates the wire, because of its own weight, has the deformation of 0.0343 inches. If we add a 70 pound, 70 pound to add to the wire, it's gonna have a deformation of 0.683 inches as well. So its own deformation and the deformation caused by the extra weight is going to be our total deformation, right? And D, the maximum load P, that this wire can safely support at its lower end if allowable tensile stress is 12,000 psi. So to find the maximum load that can be safely supported, we calculate the maximum stress due to the weight of the wire. So let me grab another color. sigma t equals P over A, right? So what do we have here? So the rate, which is 7 0 703 pound over the area of 0.0123 square is 572 psi. All right, so the proportional allowable stress that remains to resist the P is 12,000 psi, as the question says, minus what we have here, 572 psi equals 11,430 psi. So allowable load could be calculated as P equals A. We just change this because you won't have to P, yeah? We want P, right? A sigma T. So A is 0.0123 square inches and 11,430 psi. And the final answer is 140.6 pounds. Example 9.20. A steel bore having a cross-sectional area of 1.0 inch square is suspended vertically and subject to a load as shown in this figure. All right, the total length of bar is 7 feet. Compute the total elongation of the bar. Use a modulus of elasticity of 29 million psi. Neglect the weight of the bar. All right, so it says neglect the weight of the bar. If it didn't say neglect the weight of the bar, we had to do it like the example before. But since it says neglect the weight of the bar, we don't do it like that. So it is pretty simple actually. So what do we have? We have A, which is 1.0 square. We have different L's. We have modulus of elasticity of 29 million psi. So what do we have to do? We have to know, we have to calculate how much this is gonna elongate due to this weight, and how much this part is going to elongate due to this rate, and how much this part is going to elongate due to this rate. Then add all this elongation together. All right, so let's first calculate the elongation of this part AB. Okay, so AB elongation, or delta equals PL over AE. So P, which is 6,000 pounds. How much is the L? Is 1 feet. But we don't want feet, right? We want inches, so we have to multiply it by 12 inch over feet. Okay. And how much is our area? Our area is 1.0, which is square modulus of elasticity of 29 million psi. Right? Answer is 0.0028 inches. So this part is gonna elongate this much. Now part BC, right? Let's see how much part BC is gonna elongate. C equals same formula, PL over AE. Right? So how much is P here for this part? Here is 4,000 pounds and 2 feet, 12 over, which is the cross section area, 29 psi. Right? The answer is 0.0088 inches. And then finally we have to calculate how much elongation this part is gonna have, right? CD delta PL over AE. So it's gonna be so 1.0 to square root 29 million psi equals 0.0215 inches, right? And the total elongation is 0.0028 plus 0.828 plus 0.15. 0.0322 6 inches.